So as you know, this is actually, I don't use PowerPoints on this. I actually do Prezi. So you're going to see, if you're motion sickness, I'm sorry, it's going to get crazy. But anyway, so first things first, we got to talk about the language of chemistry. Before we do all that, we got to do a lot of preliminary stuff. We're going to talk about scientific method, difference between different chemical changes and physical properties, density, and obviously how to actually do some dimensional analysis. So what? Yes. So first thing you got to do is have a purpose, which means you got to ask a question. How technology has been advanced and how science and research and even private investigators investigate people all follow this little process, the scientific method. It's a little varied, but I've shortened it down to make it as simple as possible because I crammed some steps together. First thing, you got to have a purpose of where you're going to go. You got to question what's going on. Number two, you got to have a hypothesis. That's always the second step. Always the second, never the first. It's where you have an educated guess. It's where you got to actually make a prediction. And this is the problem. A lot of people try to fit their data to their prediction to prove themselves right. And that's not science. That's, you know, illegal. There's nothing else to really say about that. But a lot of scientists have been arrested or been fined millions of dollars because they took their data and to try to make it fit their hypothesis. And that's not real science. If you get something wrong or something that doesn't work out right, you figured out a way for it not to work out right. Okay? I remember them saying something about Thomas Edison failed 1,000 times to make a light bulb. Well, he didn't fail 1,000 times. He found 1,000 ways not to make a light bulb. There's always that one time that actually works right. And sometimes people hit it first time. And most of the time, though, in this class, you're not. I hate to tell you, this is the depressing part. I'll get to a little meme here in a second. So you're going to do, after you make your educated guess, you're going to gather up an experiment or form some kind of process that you're going to go by to test this. If you watch Mythbusters, they do this all the time. They'll do a small scale experiment and try to build up to a bigger scale, and then they'll just blow things out of proportion just for fun. That's what I like about it. You gather your data, and then you interpret it to form a conclusion. Here's the problem. Or not a problem, actually, but I do this. Why do you think I'm going to make you do lots of surveys? It allows me to gather data about things, to actually get an idea of the populace. Why do you think day one I made you come in and do a survey? I learned out that about 80% of y'all play games on your phones, and about 60% of you have a job after school. That there gives me an idea of the whole population of what I'm dealing with. So when somebody comes to say, well, why are you doing YouTube videos? Well, I said, now most of my students have a job after school. They can view them at their own convenience. When you get into lab on Wednesday, you're going to be doing this. You're going to have an expectation, an observation. You're going to question everything. You're going to have your hypothesis. You're going to predict. And then you're going to do your experiment. And then you're going to get your results. And you're going to be like, yes, A+. In science, it usually doesn't work out this way. The first 5 happen. And then you get this result. So my advice to you is just because you fail once doesn't mean you're dumb. You just need to try again. A lot of people don't get it the first time. You're going to have to go back and try again. So the cycle is never ending. You're supposed to actually, when you get done, you're never really done. If you ask any researcher in college, especially when I get the graduate students to come in, they're going to tell you it's like a never-ending process. It's a lot like Dante's Inferno, where you're tortured over and over and over and over again. They don't do one experiment and get their doctorate. They have to do this over and over again. And in fact, they'll spend a whole year gathering data and then find out later that whole entire year their data was wrong. And then they got to go back again. And it's not it sounds depressing. It really does. But what you need to look at it more in terms of how much of an impact you're making. You might spend this much time to begin with, but if you go back and do the experiment again, you should get through it quicker at a shorter time every single time you do it. And if you do it a third time, you should be getting quicker and better every time because you have learned from your previous mistakes. And soon enough, you develop a whole process which is actually very, very quick compared to when you first started. That is actually the whole idea of doing this cycle over and over again. So yes, you're not supposed to get it right the first time. Especially in this class, a lot of people are going to figure out that I'm going to make a 70. But you're going to get better. Every time you go in the lab, you're going to have different things. You're going to have a variable and a control. The control is going to be something that is kept the same. You're not testing it. You're leaving it be. The variable is what you're mostly going to be testing. If you do it at a larger portion, that would be the group. And then if, you know, obviously you're going to have a control group to keep it the same and see how much, how far you've gotten. So now we're getting to some more little things. We've got to pick back up where you left off on your 7th grade and 8th grade class. What is energy versus matter? Okay. It's not too bad. Energy is capacity to do work or produce heat. Do you get hotter when you work out? Or when you run? Yeah. That's because your body is releasing energy. You got to have energy inside you, otherwise you'd be dead. You know, you have a lot of potential energy. You got to consume other food and things because you can't synthesize it yourself. Unlike plants, they can make their own energy due to the sun. But we got to consume the plant or another animal to actually have energy. That's why you must always eat. Who knows? But anyway, the main thing you need to know is that the law of conservation of energy and the law of conservation of matter, they're actually the same definition. I don't know if you noticed that. Energy is neither created nor destroyed, but transferred. Down here it says matter is neither created nor destroyed, but transformed. What does that tell you about the relationship between energy and matter? If neither one is created nor destroyed, how are they related? Well, if I can't get rid of this and I can't make it, and if I can't get rid of this and I can't make it, are they related? Mind blown. Yeah. Einstein, guys. E equals mc squared. Energy is equal to matter. So it turns out that matter is actually stored energy. If you concentrate energy into one area very, very much, it turns into matter. That's where matter theoretically comes from. Notice I'm saying theoretically. But this, and we'll talk more about how that gets into dark matter and antimatter and all that. In other words, this is great because whenever we do experiments, we can take the mass of something beforehand and the mass after and get measurements. So, let me ask you this. I have a pot to water. Right here, there you go, yes. And it weighs 10 grams. With me so far? Water weighs 10 grams. Okay? I heat it up. That stands for heat, by the way. I heat it up, and I weigh it again. Okay? Now it weighs 7 grams. Did I create or destroy matter?
Transferred.
Okay, so here's the question. Many people think because it lost mass that I destroyed it. Okay, but look at the law. Law of conservation of energy, law of conservation of matter. It can be neither created nor destroyed, but it can be transformed or transferred. So what happened to the other 3 grams? It evaporated. So it actually is somewhere in the air. 3 grams is. And many people have a hard time imagining that. It's a gas. Gases are lighter than air, so you're not going to be able to have it come back. So that is actually a very good way to actually look at this. Can I get the 3 grams back in there? Yeah. Well, I mean, if I collected it and put it back in. Condensation. You know, whenever you get up in the morning, you'll see water on the side of your window. That's condensation.
So you could get that exact 3 grams of condensation back?
Mm-hmm. If you, the best way to do it is to actually have a container around this, and it would condensate back, and then it would fall back down. That's actually how water purifiers work. Is that, you know how you got bacteria and all that in it? If you boil water, you just collect it back and or distill it, and it actually gets rid of some of the bad stuff that's in it. That's how to get really, really pure water, is to boil it and distill it down a tube, and it'll come out. Okay, so matter is anything that has mass and volume. I want y'all to go ahead and make the connection here, matter and mass. How do we measure matter? We do it by mass. What is the units of mass? We just kind of did it. Grams. There we go. So that's the unit for mass. What's the unit for volume? You're close. Kilograms is mass. So you can say grams, kilograms, milligrams, that's all grams. Think about volume, liquids.
Milliliters or liters.
Milliliters or liters. Y'all may say quarts and things. We do that in America. But we're going to say milliliters for right now. That's going to be something for tomorrow we're going to bring up. So for us to measure matter, we're going to usually need these two guys. We're going to need to have the mass, which we put on a balance, and we're going to need the volume, which we usually put in a graduated cylinder. Chemistry is to study the matter and change it undergoes. So if we're studying matter, we're going to need these two guys. You're going to find out a lot of the units you're going to get is going to be mass and volume. And you're going to get sick of it. But those are going to be how we exchange it into other things. So volume is the amount of space an object takes up. Mass is the amount of matter an object takes up. So now this gets us to a big question. In America, since we're talking about different places, America, we use weight. When you get on a balance or a scale, I'm sorry, when you get on a scale, when you get on a scale, you're measuring yourself in weight or pounds, right? Okay. So this begs that there is a difference between mass and weight. Let me give you an example here. Let's say you're on Earth and you're going to go to the moon. Okay? Is gravity bigger, or is there less gravity on the moon? Yes. Okay, y'all know that. So, which means that's going to affect your weight. Okay, if I weigh 210 pounds, I've actually lost weight, but I'm not going to talk about that. If I weigh 210 pounds on Earth, I'm probably going to weigh 60 pounds on the moon. Okay? However, let's say I weigh 200 kilos on Earth. What am I going to weigh then on the moon? 50? Actually, I'm not going to change. That's the difference between the two.
So gravity affects weight.
Gravity is affecting your weight. So the whole 9.8 meters per second is actually what's pulling you down right now. That's affecting your weight. They said you could lose weight if you get on a balance and you raise your hands above your head. You might lose 1 to 2 pounds. But I will tell you, this is the reason why in this class we're going to use mass. It's because it is universally the same, no matter where you go. Because if you think about this, if I lost mass going to the moon, if I lost weight, then shouldn't I look different? Yeah, I'd be, like that. But I wouldn't. In fact, astronauts, when they go up there, they're going to have the same mass. So that's why we actually do it. Mass is more universal. So the simplest form of matter, you can't break it down any further. That's where we get our periodic table of elements. Those are the most simplest forms of matter we found. Yay. However, the big thing you need to figure out is the differences between these two guys. That an element versus a compound. A compound is multiple elements. It's 2 or more chemically bonded together. So this is where we get to quiz time. Okay? So if I say Fe, element or compound? All right, so ask yourself, is there just one or more? There's just one. Okay? So if it's just one, it's going to be an element. Yes?
Wouldn't NaCl be a compound?
Yes. So NaCl is salt. That is a compound. You are right. That is a compound. Again, I can't see up here.
We're writing all of these, right? Or just the ones you have to...
Well, I'm going to give you examples later also for these. But if you want to write them down, you can. It doesn't hurt. But this is a good example here. Even though there are 2 elements here, but they're together. That makes a compound. What about H2O?
Compound.
Definitely a compound. So you really got to ask yourself, is there more? Is there 2 or more, or is there just one? I can even say this up here, gold. Au. That is an element. Now let's get a little crazy. All right, iron can rust. In other words, you oxidize it. This is the chemical formula for rust. Element or compound? Compound. That's a compound. So why you got to tell the difference between an element and a compound? Well, also it has to do with language. So for example, elements, we don't say we have this many molecules of gold. We don't have this many molecules of iron. We don't say molecules. We say atoms. So if I have one atom of gold, we would say atom here. We would say atom here. However, if it is a compound, we say molecules. So be very careful with your language on there. That is very important. Sometimes I'll write. Say that again. Element and a. Right. So atoms come together to make molecules. Or compounds. So why are we dealing with the whole word of atoms then and compounds? Yes, basically I'm telling you these two guys are synonyms. These two are synonyms. But this is the unit we use to measure compounds in. This is the unit we use to measure elements in. Does that make sense? Okay. So, for example, at the very bottom, I love actually the little example down there. It says there are many atoms of copper in a penny, and there are many molecules of water in a drop of water. We don't say atoms of water. That's one of those, I don't know, English words. All right, here we go. Properties of matter.
Do we need to write that one down?
Oh yeah, all of it. So I'm going to zoom into both of these, so don't try to squint right now. But I'm just going to show you the difference between properties of matter versus the changes. Changes are easier, in my opinion. Properties are a little bit more confusing because you got to actually break down the words. We're going to look at chemical versus physical.
So you need to make sure to write down the example.
Oh yeah, definitely, definitely. Actually, the examples are more important than the definition because those are the kind of things. So tomorrow for bell work, when y'all come in, I'll give you a sheet that has to do with practicing these two. So remember in your notes where to find these. Mainly I'm going to ask you, is this a chemical or physical? Now properties are a little bit different from changes because properties is the potential. Changes means something that actually happened. Changes are a little bit more fun. So for example, if it has the ability to be set on fire, like wood, or react with another substance, it's going to be a chemical property. Makes sense. You're changing the identity of it. Physical properties, though, are more things that can be observed without altering the substance. In other words, the color, the texture, density, melting or boiling, shape, more tangible, I would say, for those guys. These are things that you can actually see, touch, smell, things like that.
So we need to make sure we get the examples.
Yes. Actually, those are more important. Actually, this is a little bit easier to understand because you can visualize these. And yes, the things in the parentheses are very important. Chemical changes. Actually I had a student last year come up with this. This is actually a good idea. She said that how she tells the difference between the two is that can you go back? She always asks, can I go back if I look at these? One of them, for example, if I burn a piece of wood, can I go back to that piece of wood? No. Chemical change. You've altered the identity. However, if I chop the piece of wood in half with an axe, would that be chemical or physical?
Physical.
Physical. Usually physical is what you physically had to do it. So changes that do not alter the identity of the substance: tearing, cutting, bending, crushing, dissolving, phase changes. And I'm actually going to discuss some of these because dissolving gets people. Dissolving, people think that is a chemical. That is not. That is a physical.
But you're not doing it.
Well, I'll give you some examples. So let's say, I don't know if you've ever tried this, but let's say you take some salt and you dissolve it in water. Okay? Can you get the salt back?
Yes.
Yes. How do you do it? You boil the water until all the water is out, and then you're left with salt. So you can go back if you do dissolve something. Yeah.
You do that with sugar?
You can do it with sugar. You can do it with sand also, but sand is already not dissolved in water. So, I mean, you could do it still with that too. That's all the distilling process. Distilling is basically going backwards from dissolving. Crushing, y'all already know that. It's physical phase changes. When I say phase changes, I'm talking about what? The what? The moon. No, you're not wrong there. What are the 3 states of matter?
Liquid, solid, gas.
Okay, so we got liquid, and we're going to go more into them here later. Solid, gas. So, I have a piece of ice, and how do I get it to be a liquid? Melt it. Increase the temperature. And then it's a big pool of water, okay? If I continue heating that, what's going to happen? It's going to turn into specks, or gas, or whatever you want to look at. So what's going on is this. Let me ask you. When it's in the liquid phase, is it what, I mean, I said it was, what compound is it? That's water. When it's in its solid phase, what is it? Ice, which is water. When we boil it and turn it into steam, what is it?
H2O.
It's still H2O. Have I changed the identity of the water? No. It is still H2O. It's just changed its phase. Okay? So that is a really good example to actually put in for phase changes. And that's something we're about to talk about here. But note that I did not, when you heat it up, even though I added energy to it, I did not rearrange it. I did not change its identity. It is still water. Okay? Can I go backwards? Yeah. So if I added heat to get it to evaporate, what do I need to do to make it go back to ice?
Freeze it.
Freeze it. Go back this way. So that's really the whole rhythm. Now, some people do ask me this. What about plasma? Okay, and plasma used to, and this is a debate right now. Technically, there's 4 states of matter, and yes, plasma makes up 99% of the universe, but it's really kind of crazy. All plasma is nothing but a really, really hot gas. Okay, so let's do some pictures. Yes. All right, chemical or physical change? Ask yourself this, can you go back? No, you can't get the forest back once you burn it. Smokey would be very upset. The bear, not the dude from TV. What? You can rebuild it, but you couldn't like immediately jump back from the fire to the, or from the ash to the woods. All right, so let me explain what you're seeing here because it looks like it's doing some stuff. This is reacting with an acid. Listen, key word there, reacting. Chemical or physical?
Chemical.
It is chemical. Also, notice this. Bubbles. Bubbles means what's being produced? Bubbles?
Yeah.
Gas. You're right, it's a gas. For example, let me jump back here. So take a look what it says. Indication of a chemical change. New gas being produced. Whee! Oh, would you look at that? It's in your notes. So bubbles means gas. New gases are being produced. That's a chemical change.
Question, you know how like you pour peroxide like on a cut or something and it like bubbles up?
That's a chemical change. You are correct. So yeah, did y'all hear what she said? So you know when you take hydrogen peroxide, you put it on a wound to clean it, it bubbles. That's a chemical change. It's actually cleaning everything. I will warn you though, don't clean something too much with peroxide because you'll kill off your normal bacteria. Like some people boil out their ears with peroxide. They'll do it like once and that's okay, but if you do it every day, your normal bacteria that lives there will die. And then you will have an ear infection.
I do that with like, because I just got my ears pierced. I do that every day.
Now in the ear or on the outside? Oh, that's fine. It's in a small damp area because then you can have a fungal infection in your head. And that's not good. I'm not joking. It's actually, you'd be surprised how many people get fungus infections.
Is that an egg?
That is an egg. Cooking an egg. Chemical or physical? Can you go back to the yolk?
Oh, it's physical.
Yeah, you can.
No, you can't. Proteins are already rearranged. You can't get them back. Take a sheet of paper and turn it. It is physical.
What about tape?
Sorry.
How are you supposed to go back to that?
You can tape it. Oh, now this one's a good one. This one's a good one. Okay. Dissolving sugar in water.
Physical. You get it back.
Can you get it back? You can. That is a physical, actually. That's actually a good one. Melting ice cream. Chemical or physical? This one gets people. Is it a phase change? You're going from a solid to a liquid. So that's physical. Now, if you left the ice cream out to spoil and smells sour, then that would be chemical. But that's a physical. So phase changes, no dissolving. Dissolving and phase changes gets people on this one. So be careful with those because they look like reactions, but they're not. I did on that. Yeah. All right, second step to scientific method is always what? Hypoponymous. Yes. Okay, so hypothesis. Number 2 says the blank group is the group not being tested. That would be your control. Yeah. Number 3, all chemical reactions either require energy or give it off. True or false? True. This is true because it can absorb, which makes it cold, or give it off, which is hot. So that is very, very true. Number 4, sodium chloride, NaCl, also known as table salt, is an example of an element or a compound. Compound. Why is it a compound? It's got at least 2 elements in it. So that makes it a compound. Number 5, there are blank pieces of, there are many blank in a piece of iron. What did we say? Okay, so if it's just iron, is that an element or a compound? Element. That is an element. So do we do elements in atoms or molecules? Atoms. Okay. Number 6, melting a piece of ice is an example of what kind of a change? Physical. Okay. So let's ask ourselves. It is physical, but ice, okay, is that a solid, liquid, or a gas? Solid. Solid. So you're going from a solid to a liquid. Okay. Let me ask you this. What is the chemical compound of ice?
H2O.
Okay. What is it in its liquid form?
H2O.
Did you change the chemical composition? No. In fact, if you kept boiling it into vapor, or vapor, as the British say, I don't know if that is even right. They like to put U's into places. I probably misspelled it. But it'd still be H2O. And this is actually a good point to bring up because there is going to be some test questions based around this. What happens when you boil water? You still have water. It's just in a gas state, okay? Gas, liquid, and obviously solid. People think, and this is okay, this is a misconception. People think when you boil water, and I'm writing this down for y'all now, they think this happens. That is incorrect. Because hydrogen is extremely flammable. So is oxygen. If you boiled water and got those 2 compounds, you would blow up. Okay? And I'll talk about the Hindenburg and we'll talk about that too. But do realize when you boil water, that does not happen. Okay? When you do boil it, it just goes from a liquid to a gas. Okay? This is very big. You would not believe how many people get that wrong on the test. Whee! So let's talk about states of matter. We already talked about a few. First off, when you see solid, liquid, gas, what do you notice the big difference between all 3? Besides the amount. Okay. Solid's more compact. What did you say? Some's more separated as you go to the right. Y'all said something over here. Did anybody say anything about the space? Yeah. So one of the biggest things is the shape and the space that you see in there. And we say space is going to be more about volume because space has to do with volume. But anyway, Each one is a little bit different. Obviously, we already went through if you heat it up, it's going to go to the right, and it's going to separate a little bit more. Therefore, which one of the three up there has the most, and I'm going to use this word very carefully, kinetic energy? Which one has the most kinetic? The gas. Why? He's bouncing around. He's doing all this kind of stuff. It's a lot like kindergartners jacked up on Mountain Dew. So y'all are more like a solid right now. Y'all are in line. Y'all are kind of being still. But here's the biggest thing. Gases are always in motion, because y'all just said that. Liquids, are they always in motion? Yes, actually they are. They're moving around. They're kind of like in a mosh pit right now. Excuse me, pardon me, coming through, at a concert kind of thing. So they're all kind of compact together, but they're moving around. Solids, are they moving? They look like they're not, but they are. Very little, very teeny tiny. So let's actually get some of these definitions. So solids are moving, but very lightly. Slightly. Sorry, not lightly, slightly. So even though you have something frozen, it's still vibrating very little bit, but not very much. For example, if you take ice, put it in a microwave, y'all do know how a microwave works, right?
No.
Yes.
Sends in microwaves, and what it does is make all the water molecules start shaking up, vibrating, and the more they vibrate, the more energy they release. And that's how things cook.
Yeah.
Well, if you were microwaved, yes. But eating microwave food, some people had that, like, could I get cancer from eating microwave food? That's actually not true. But, I mean, because it's microwave radiation is the reason why. The radiation really scares people. Definite volume, definite shape. Whee! Liquids. Liquids have a definite volume, but liquids take on the shape of whatever they're in. So if I take water and I pour it in my cup, it becomes the shape of the cup. If I pour it in a bowl, it becomes the shape of the bowl. That's one great thing about liquids is it takes up the shape, but it still has a fit volume. Okay, flow of particles around each other. Examples are water, alcohol, syrup, gasoline. Last but not least, gas. Neither is definite. We're actually you'll see it here in a second. So no definite volume, no definite shape. So how do we measure these guys if they don't have a shape or a volume? Yeah, actually you're right. So that's the problem with the gas. If I told you to go in there and get the mass of oxygen gas, you couldn't do it. You'd have to turn it into a liquid. And to do that, you're going to need some pressure and lower the temperature and things like that. But we have a whole unit far from now, like many months, like 2 months from now before we even talk about gases. Well, before we study gases, sorry. A balloon? Right, before it pops. Another issue is that some people think you can put air in a balloon, put it on a balance, and get its mass. The problem is, though, it's fighting against the gravity. And so that's going to cause a little bit of problem. Liquids and solids we can both get the mass of. But gases are a pain in the butt. We got to somehow trap them. So you got to take consideration pressure and the volume and things like that. That's a good test question. Let's actually take a look at something. So fill in the following chart. Write in definite or not definite. Or yes or no. I don't really care. So for example, you see solid column? You need to tell me what its shape is, if it's definite or not, or what its volume. All right, let's see how y'all did. Whee! So, solids are both definite shape, definite volume. Now, think of shape. That's like pouring it into something. Yes, you could pour salt in there, but it won't take up the entire shape of the container. It has a fixed shape. Liquids, however, do not. They can mold to whatever, but you can get its volume. If you're drinking water right now in front of you, or Powerade, you can notice that it has a volume. But it's taking up the shape of your container until you freeze it. And last but not least, gases are a pain in the butt. Neither one. So we got to do a lot of other factors in terms of studying gases. That's where Unit 7 comes in. Unit 7 is nothing but a gas. Okay. So we got to go through this last little thing of classifying matter. Whee! Oh, okay, so I got to talk about this. I'm sorry. So water changes we already talked about, but did you know that the butane in your lighter are in a lighter? Not saying they all have a lighter, but if you ever lit fireworks, you use a little butane lighter. The gas inside is a liquid. You can look and see it. But when you open it up, it's a fire, but let's say you didn't light it on fire. It's a gas. So this is what kind of tells you is that if you put pressure under a gas, it'll turn into a liquid. So you can change the state of matter without changing the temperature. You can change the pressure. Could I then take a gas, keep compressing it, even through liquid, and turn it into a solid?
Maybe.
Yeah, actually you can. You know what? What do you think dry ice is? Frozen CO2. So actually, if you ever take frozen CO2 and put it by plants, the plant will grow stronger because plants breathe CO2. Oh, yeah. So we already talked about water changes. We talked about pressure and temperature. That's one reason why Unit 7 is all about the temperature and pressure. Obviously, that's going to be a lot of math. So matter can be broken down into many different things. You can break it down into mixtures or pure substances. Pure substances get to what we were talking about earlier, elements and compounds. And you already know what elements or compounds are, but I'm going to go over them again just in case. Mixtures are on a bigger level, like huger level. Yes, I said huger. But it's better just to give you examples as we go on. So matter. All matter is either a pure substance or a mixture of pure substances. Whee! All right. So now that gets us. Let's talk about the pure substances. Shh. Pure substances can be elements or compounds. Either one. Compound is, well, not just two, but two or more. So that's a big difference. And now for more specific examples from earlier. So elements, simplest form of matter. Example, copper just by itself. Iron just by itself. Carbon just by itself, or sodium. All are found on the periodic table. So if you take one of those off the periodic table, you have yourself an element. Oh, God. All right, chemical compounds. I'm surprised y'all even know that movie. All right, now, chemical compounds can be, obviously I already know these. NaCl is table salt, H2O is water, potassium sulfate is potassium sulfate.
Have you written any of this?
So in case you missed this earlier. All right. So mixtures, there are two types of mixtures. Do y'all really need to write that down?
No.
Okay. I just,
No
in
way.
case you're like, wait, let me write it down. So two types of mixtures. There are the homogeneous and the heterogeneous. Not homozygous and heterozygous from your biology class. It is the same terminology though, or similar definition. Homo means same, hetero means different. Okay? So homogeneous mixture is going to be something the same all the way through. In other words, you can't tell the difference. I'm going to give you a hint on these guys, okay? Homogeneous mixtures are ones where something has dissolved in it. So, salt water. Can salt dissolve in water?
Yes.
Can you see the salt once it's dissolved in water?
No. No.
So, that's a homogeneous mixture. Sugar, does it dissolve water?
Yes.
Yes. Can you see the sugar in there?
No.
Unless you put a bunch in there, you can't. Same thing about pudding. So chocolate pudding, vanilla pudding by themselves. They're homogeneous. Okay. All right, let's test you on this one. Vanilla yogurt. Same all the way through or different?
Different.
It's the same.
It's the same. It's just like pudding. However, if I said strawberries in the yogurt, that's different. You could see two different things then, two or more. Here you cannot see a difference. So I'm going to give you a hint. If it dissolves, it's a homogeneous mixture. Okay? So this gives me to my next point. Does sand dissolve in water?
No.
No. So you could see the water and you could see the sand. So therefore, that is a heterogeneous. So So there are many things that can represent a heterogeneous mixture, such as, well, chocolate chip cookie is a good one. You can see the cookie and the chocolate chip. Salad's a good one. But even though it's not up there, you might want to write down sand and water. That's a good basic one. Bless you. All right. Number one, we look at these have a definite volume, but no definite shape. Solid, liquid, or gas? Liquid. I heard somebody say something. So what does a solid have?
Definite volume and definite.
Both definite. This one has?
Nor.
Neither. Yeah. Nor. That's what's right too. Number two, can be elements or compounds. This is a crazy question. Yeah, if you look through your little chart, it actually was one of the things. It'd be pure substances. Remember, because these two break down in these two guys, impure substance wasn't even on there. And mixtures would be the heterogeneous and homogeneous. Number three, pure gold is an example of oh, I should have said and, but that would have gave it away. Of an element. Especially also it says pure, so that gives you a good idea it's going to be on one of these two sides. All right, we've been through the difference between element, compound, and all that kind of stuff more often. Real quick, just to make sure everybody's got this. Sand and water would be which of these two?
Hetero.
No. Hetero.
Because they're different.
Because they're different. You can see the difference. Sand does not dissolve in water. And if I said salt and water? Homogeneous. Okay. Good examples. Number four, an example of a homogeneous mixture is, I think I kind of gave it away, didn't I? Well, let's see. Does this dissolve in water? Does this dissolve in water? Can you see two different things in this one?
Yeah.
Okay, is there multiple things in this one? Yes. So the big answer would be this one. That's actually a very good one. Okay. Well, that's all I got to have for y'all today. Any questions so far? Okay.